Hey everyone, how you guys doing today? So we're moving on to chapter 4 now, uh, which is all about functions and interfaces. Just gonna move this a little further up. Just move it out of the way, hopefully. Functions and interfaces. Chapter 4 of Think Python. This chapter introduces a module called Jupytertle, which allows you to create simple drawings by giving instructions to an imaginary turtle. We'll use this model to write functions that draw squares, polygons, and circles and to demonstrate interface design, which is a way of designing functions that work together. I'm not sure what this is about. Okay. Make turtle creates a canvas. Okay. So we import it. Now we can use the functions to find a model like make turtle and forward. Make turtle creates a canvas, which is a space on the screen where we can draw, and a turtle, which is represented by a circular shell and a triangular head. The circle shows the location of the turtle, and the triangle indicates the direction it is facing. Forward moves the turtle, gives a line segment along the way. Distance is in arbitrary units. The actual size depends on your computer screen. You'll use functions in the Jupytertle module many times, so it would be nice if you do not have to write the name of the module every time. That's possible if we import the module like this. Yeah, so by the way, this, taking a sidebar because I don't really care about this Jupytertle stuff, but when you do from import something, that's actually better practice, because going back to what we spoke in the previous episode about scopes, when you import something, you bring it into the scope. So if you import an entire module, you're importing everything that is in that module scope. So it's better to actually import the things you are going to use rather than literally everything, because that just pollutes the namespace and makes it harder to do variables and stuff like that. Okay. So version of the import statement imports, so it's basically, that's what I'm saying. It's like, so for example, if you want to import pi from math.py, and that's the only thing from the math module that you're using, then you can just do from math import pi, rather than importing the entire math module and then that thing's in your namespace, and like, why have it be there if you're not using it? Make so from Jupytertle import make turtle forward, make turtle forward 100 modules, so we can call them. The version of the import statement imports make turtle and forward from. Okay, yeah, okay. Because it imports it from Jupytertle, you don't have to say the whole thing. So that's the other nice thing about doing it this way. It's like if you're only using a few things, it makes the code slightly less verbose. Jupytertle provides two other functions we'll use called left and right. We'll import them like this. Okay, what does left and right do? So forward 50, left 90, forward 50. Okay, so that's just the left is like 90 degrees. The program makes the turtle east and then north, leaving 2 line segments behind. Before you go on, see if you can modify the previous program to make a square. Screw making a square. I'm gonna try and make a triangle, actually, if I'm understanding this correctly. Because I am having fun. Forward 50, left 60, no, not 60, 180 minus 60, so left 120, forward 50, left 120 again, and then forward 50. I believe this will make a triangle. Yup, there it is. I told you guys. An equilateral triangle. Right, so I like pictured it like when it came here, and that's why I did left 120, because 60 would not turn it enough, and I'm just doing left turns. I'm sure there's like move right as well. I could have also, I think, turned first and then done it. Like I could have turned left 60 and then forward 50. But then I'd still have to turn this way. Would that be left again? Or that would be left. I could do left again and it'd be a weird triangle. But anyways. So this program moves the turtle east and then north. Leaving 2 line segments behind before you go on. See if you can see. So I'm just gonna. This is how you do the square one, which I didn't want to do. Because this program repeats the same pair of lines 4 times, we can do the same thing more concisely with a for loop. Okay. Yep, that's true. Encapsulation and generalization. Let's take the square drawing code from the previous section and put it in a function called square. Make turtle square. Boom. Wrapping a piece of code up in a function called encapsulation. One of the benefits of encapsulation is that it attaches a name to the code, which serves as a kind of documentation. Another advantage is that if you reuse the code, it is more concise to call a function twice than to copy and paste the body. There you go. Those are both, this is just further talking about functions and their usefulness, and encapsulation and inheritance is essentially, it's very important to modern object-oriented programming, right? I want to look up the formal definition of encapsulation. Encapsulation is the formal concept of binding data and the methods that operate on that data into a single unit known as an object, and restricting direct access to some of the object's internal components, right? This combination of bundling and hiding details is a fundamental principle of object-oriented programming. There you go. That enhances data security and maintains the integrity of an object state by preventing unauthorized access or modification. So that's a mouthful, and it does imply a lot, and I'm not sure if I understand all of the implications of it. But yeah, that's essentially what that is. In the current version, the size of the square is always 50. If we want to draw squares with different sizes, we can take the length of the sides as a parameter. So this is basically the same square function as before, except now we're giving it a parameter so that we can make 2 different squares of different sizes, right? Which is another, so many reasons. It's just like packaging something together, right? That's essentially what a function is. You're just putting together code into something. And honestly, a lot of computer science and programming is basically this, especially in this day and age. Now, there is also functional programming, which tries to avoid a lot of the things that OOP does for certain performance gains in some situations. But regardless, even there, like, these concepts still remain important. So yeah, that's just like a small aside. That doesn't matter to someone who's actually reading this as a beginner. Adding a parameter to the function is called generalization because it makes the function more general. With the previous version, the square is always the same size. With this version, it can be any size. If we add another parameter, we can even make it even more general. The following function draws regular polygons with a given number of sides. A regular polygon. Okay. 360 divided by 3. Oh yeah, that would be 120. So it would make a triangle as well. And also what's another thing that's nice is you can set up default values if you want. So for example, I can set n equals 4, aka the number of sides, and length equals 50 as the standard. So if I do want to call this function without that, I can do that as well. So I can have kind of the best of both worlds, where I write a function, I write it with parameters, and then I'm calling it in a very specific way for a very long time. I can just set up default arguments. So that's just a little nicety. Command C. I'm just gonna bring that back to normal, showcase the septagon, hexagon, I think, hexagon. Yeah, I think this is a hexagon. Now hex is 6, pentagon is 5, hexagon is 6. I don't know what a 7-sided polygon is. Anyways, when a function has more than a few numeric arguments, it is easy to forget what they are or what order they should be in. It can be a good idea to include the names of the parameters in the argument list. So these are sometimes called named arguments because they include parameter names, but in Python they're more often called keyword arguments, not to be confused with Python keywords like for and def. This use of the assignment operator equals is a reminder about how arguments and parameters work. When you call a function, the arguments are assigned to the parameters. Okay, so yeah, essentially we can pass arguments in as keyword arguments. So that makes the code more readable for other people. And there's a decent amount of nuance here with keyword arguments and positional arguments and star args and star quargs, wherein you can pass in a mixture of like positional arguments. You can just be like 7 and then comma length 30 in this example, right? Like I believe that would be valid as well. If I just do this, yeah, see. But you can't do, I can't do this. So 7, see, that will be positional argument follows keyword argument. So you can't have, if you're gonna give like a mix, you're gonna wanna always do your positional arguments first, right? And also the person who writes the function can enforce that all the arguments need to be given as keyword arguments by putting star at the beginning. So all the arguments are now keyword arguments. So now if I run this, okay, Polygon takes 0 positional arguments, but 1 positional argument was given and 1 keyword only argument were given, right? So I gave 1 as this thing, but it takes none, right? And here's the thing, star can be put somewhere else. So I could put star here, and then I could signify that length always has to be given as a keyword argument. So running that and running this, now this will work, right? So that way, wherever you place the star, all the arguments after that need to be given as a keyword argument. And if you, that is what you can enforce as the function writer. And if you are someone who's calling someone else's function or your own function, whatever, the calling operations would be, you have to do all your positional arguments first and then all your keyword arguments if there is any scope for positional arguments. Yeah, that's just your general rule of thumb. So I said I wasn't going to go into that, but I went into that anyways. They're sometimes called named arguments because they include the parameter names, but in Python, they're more often called keyword arguments, not to be confused with Python keywords like, okay, we already read this. This use of the assignment operator is a reminder about how arguments and parameters work. When you call a function, the arguments are assigned to the parameters. Right, yeah, so when you're calling a function, so if I give it 7 and 30, it's going to be assigned to these variables that are then used inside the function. There you go. Approximating a circle, Jesus Christ. Suppose we want to draw a circle, we can do that approximately by drawing a polygon with a large number of sides, so each side is small enough that it's hard to see. Here's a function that uses a polygon to draw a 30-sided polygon that approximates a circle. Okay. So circumference equals 2 times math pi times radius, which, yes, 2 times pi, 2 pi r is how you get a circumference. And then you say 30-sided thing, length, circumference, polygon, and length. I'm going to run this, and I'm going to run this. What's the issue? Oh, I'm going to revert polygon back to its original state because it is being used here and they're losing their mind, which makes sense. Oh, that's actually a very nice circle. I just want to see this again because, oh man. I just like that little turtle. It's so cute. I feel like this is something from maybe Basic. I remember something like this in Visual Basic like long ago when I was a kid. That's why like this is triggering some memories maybe for me. I don't know. A function might take a long time to... Okay, circle takes a radius, blah, blah, blah. N is the number of sides, so circumference divided by n is the length of each side. This function might take a long time to run. We can speed it up by calling makeTurtle with a keyword argument called delay that sets the time in seconds the turtle waits after each step. Default value is 0.2 seconds. If you set it to 0.02, it runs about 10 times faster. Oh, I didn't see that. I didn't even notice that. Let me just set it to run for 2 seconds. Jesus Christ, it's gonna run forever. I'm actually gonna pause the recording, go pee while this happens, and then see what it's like when we get back. All right, let's check in on our turtle. Oh, the first circle isn't even done yet. This is silly. I'm not gonna let this run for that long. I wonder what happens if I set it to 0. Can I do that? Oh yeah, it's like instant. So yeah, I don't know why that delay is there. I'm pretty sure it's there to like have the visualization happen so that people can actually see it. And also realize that when you're making the canvas object, you can pass in functions. I feel like this canvas object stuff is fun, but like, I don't know if that's a good thing to be teaching people, but maybe it is, I don't know. A limitation of the solution is that n is a constant, which means for very big circles, the sides are too long, and for small circles, we waste time drawing very short circles. One option is to generalize the function by taking n as a parameter, but let's keep it simple for now. Yeah, so basically here it's saying that because n equals 30, if you do something like and it's fixed, and if you decide to draw a really large circle, it's not going to look like a circle. You'll be able to clearly see straight lines because it's a large circle, and if it's a small circle, it's like an unnecessary amount of resolution. So, and you can, and one way to generalize this would be just to make n a parameter. In fact, I can do that like this, n equals 30. So that goes back to talking about, setting up default values, and that way I don't have to change my code here at all, and it'll still work, and I don't have to use n in here. I'm just going to comment that out. Shortcuts for commenting is Command and / or Control and / if you're on Windows, and then this should work just fine. See, I've already done this part, so that wasn't that hard, but they told you to let's keep it simple for now, so we're gonna keep doing that. Refactoring. Now let's write a more general version of circle called arc that takes a second parameter, angle, and draws an arc of a circle that spans the given angle. For example, if angle is 360 degrees, it draws a complete circle. If angle is 180 degrees, it draws a half circle. To write a circle, we're able to reuse polygon because of many-sided polygon. Okay, I'm so confused. Also, I'm like mildly in my head distracted regarding something, so I'm just going to pause the recording for a moment. All right. we already did this, going into the refactoring. Sorry about that. Now let's write a more general version of circle called arc that takes a second parameter angle and draws an arc of a circle that spans the given angle. For example, if angle is 360 degrees, it draws a complete circle. If angle is 180 degrees, it draws a half circle. To write circle, we were able to reuse polygon because many-sided polygon is a good approximation of a circle, but we can't use polygon to write arc. Instead, we'll create the more general version of polygon called polyline. Okay, so I get what they're saying. So polygon is over here somewhere, not def square. I think there's def polygon for any length and angle. They want to make it more general, so that I guess you can pass in the angle as well. N length angle, yep, that's exactly what, for I in range N, forward length, left angle. Polyline takes as parameters the number of line segments to draw N, length of segments length, and the angle between them angle. And then we call that from polygon, where we have the angle still fixed at 360 degrees, which we could then make more generic. Wait, no. Just trying to understand how these work. I don't want to spend too much time on this. That was cute, cool as all hell, but it just did. Okay. Length equals arc length divided by N, step angle equals angle divided by N. So why would going straight to polyline, so I'm not using polygon here. Okay, so I don't use polygon in the arc function. There you go. That was my major malfunction. Like, how do we build this into this into this? We're just not using. We're just going to use polyline separately and polygon separately, and just have polyline just get everything, the length and the angle, which was the only thing missing. I think. See, N and length was already given. Angle was just always fixed, right? So instead of doing that, we give it the angle. That we want. And in polygon, that's just 360 by N. I guess the major malfunction I'm having is just giving the function N, but then we're already doing that in polyline. Anyways, I'm not gonna spend too much time on whether this is the most optimized design for these functions, because that's where my brain is going right now. So essentially we made a more generic version of polygon, the original polygon function, where the angle was fixed, and made one where the angle wasn't fixed. And instead of, and we just give it that angle, and it's essentially the same other than that. And then in polygon, we pass the angle 360 by N into polyline, or in arc, we calculate the length of the arc that we want, right? So someone gives us the radius and the angle, right? That allows us to calculate the arc length. So 2 pi r is the circumference, right? And then times angle divided by 360. I don't know about times angle. Yeah, times angle divided by 360, I guess, kind of makes sense, yeah. Anyways, I would have to like draw this out if this all mathematically checks out, which I'm pretty sure it does. And then we do def circle, which is just radius, arc radius 360. So, and then here is just make polygon n equals 20, length 9. polygon, arc, circle. Why is polygon n equals 20, length 9? Yeah, okay, so polygon also does a circle, right? A little confused here. Polygon n equals 20. Why is it calling polygon first? Did I rewrite polygon? Polygon, arc, polyline. Okay. Length 9, number of sides 20. Okay, so we just give it an arbitrary size and length into polygon, which is what we were doing with circle, except we had fixed it to n equals 30 and we gave n equals 20 in polygon. And then we created the arc and then we did the circle. Okay, that makes sense. We start with working with code. We reorganized it with different functions. Changes like this, which improve the code without changing its behavior, are called refactoring. If we had planned ahead, we might have written polyline first and avoided refactoring, but often you don't know enough at the beginning of a project to design all the functions. Once you start coding, you understand the problem better. Sometimes refactoring is a sign that you have learned something, and that's true. That's very true. When we call circle, it calls arc, which calls polyline. We can use a stack diagram to show the sequence of function calls and the parameters for each one. So starting from the bottom, polyline is called by arc, which is called by circle. Polyline gets n, the length, and the angle. Arc gets the radius and the angle, and circle just gets the radius. So that's the order of operations when you call circle, basically. Because circle just calls arc, I believe. Now, yeah, it does. Radius 360. Notice that the value of angle in polyline is different from the value of angle in arc. Parameters are local, which means you can use the same parameter name in different functions. It's a different variable in each function and it can refer to a different value. Yeah, so that's true, essentially. Basically, going back to the previous conversation we had about scopes, variables defined within a function are only available within the scope of that function. They are local to the function scope, right? A development plan. A development plan is a process for writing programs. The process we used in this chapter is encapsulation and generalization. The steps of this process are: start by writing a small program with no function definitions. Once you get the program working, identify a coherent piece of it, encapsulate the piece in a function, and give it a name. Generalize the function by adding appropriate parameters. Repeat steps 1 to 3 until you have a set of working functions. Look for opportunities to improve the program by refactoring. For example, if you have similar code in several places, consider factoring it into an appropriately general function. This process has some drawbacks. We will see alternatives later, but it can be useful if you don't know ahead of time how to divide the program into functions. This approach lets you design as you go along. The design of a function has two parts. The interface is how the function is used, including its name, the parameters it takes, and what the function is supposed to do. The implementation is how the function does what it's supposed to do. For example, here's the first version of Circle we wrote, which uses polygon. And then here's this refactored version that uses arc. These two functions have the same interface that take the same parameters and do the same thing, but they have different implementations. Yeah, so I don't know if they're going to get into that in this thing. I don't think so in this chapter, but essentially this is an important concept of decoupling interface, the concept of interface from implementation, because in reality, later on, you will actually decouple interface and implementation, wherein you can have a class that defines an interface, and essentially everyone looks to that interface for the ground truth of how I call a function, and then the encapsulation, the how everything works underneath it is something that is completely obscured from them. Not just by the sake of implementing packages and things like that, but this can be really useful in large software projects where, for example, like if you have a function that, like, let's say fetches a file, right? But it's essentially the same function with the same like two parameters or something again and again, um, wherein the second parameter tells you like which place to get the file from, but that place to get the file from significantly overrides how that function is called, right? So then you have you can have an interface where it's like, this is how this function is called, you always call it like this, and then in the back end the specific function that's called can be different. That's technically an example of overloading, but it's this, a lot of things kind of follow through from understanding the concept that the interface, aka how you call a function, is actually different from the implementation. Um, Moving on to doc strings, these are simple. If you start like a triple line quote right after the function name and you write some stuff there, whenever you hover over that function, it's going to show this doc string so that, you know, someone who's using your functions can read that function later on. So for example, if underneath here code I do a escape a, okay, I was just trying to see if Google Colab had similar Jupyter Notebook things. Anyway, so now if I go and polyline, and if I hover over this function, boom, draws line segment with the given length and angle between them, blah, 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 blah. So it's just, you know, you get everything that you need that way, right? Just by hovering over the function to understand what it does. By convention, doc strings are triple quoted strings, also known as multi-line strings, because the triple quotes allow the strings to span more than one line. A doc string should explain concisely what the function does without getting into the details of how it works, explain what effect each parameter has on the behavior of the function, and indicate what type each parameter should be if it's not obvious. Writing this kind of documentation is an important part of interface design. A well-designed interface should be simple to explain. If you have a hard time explaining one of your functions, maybe the interface could be improved. Yeah, true. All of this is just true. Debugging an interface is like a contract between a function and a caller. The caller agrees to provide certain arguments, and the function agrees to do certain work. For example, polyline requires 3 arguments. N has to be an integer, length should be a positive number, and angle has to be a number which is understood to be in degrees. These requirements are called preconditions because they're supposed to be true before the function starts executing. Conversely, conditions at the end of the function are postconditions. Postconditions include the intended effect of the function, like drawing line segments, and any side effects, like moving the turtle or making other changes. Preconditions are the responsibility of the caller. If the caller violates a precondition and the function doesn't work correctly, the bug is in the caller, not the function. If the preconditions are satisfied and the postconditions are not, the bug is in the function. If you pre and postconditions are clear, they can help with debugging. So yeah, this is just more conceptually following along from that decoupling of interface and function, and interface and what's the other word? Crap. Implementation. There you go. It just naturally follows through that basically when I call this, I have to give it these things. And if I'm not giving it these things properly or in the way that it expects and it's explained to me, or even if it's not explained to me, I still need to give it in the correct way, then the issue isn't how I'm calling something, right? But if I'm calling something the correct way and then that thing is not doing what it's supposed to, then the issue is with that, right? So being clear on what are the things you need to give something, aka being very clear on what the preconditions are, and being very clear on what you expect to actually happen from the function, is just it's like what you need to actually understand and fix any issues that you have in the code, right? Because and that's, it's fine to not have that perfectly mapped out as you're writing the code, because that's actually the process of debugging, right? Is like you'll think you're calling something correctly, and then you look into the and then it's not doing what you want it to do. Then you check the documentation or whatever, and you're like, oh, okay, actually I need to call it like this. I called it like this. Oh, this function isn't actually doing what I want it to do. Am I even calling the right function? Okay, do some more research. Okay, maybe there's another function or something like that, right? Like being clear on what you want on the output and what you want on the input, right? And then doing the research to figure out what is going wrong and whether it's you or something else. And if it's something else, how to swap that out for whatever you need, right? Either if it's a function you write, or if it's like you're using a library or something like that to maybe use a different library or write your own function around it or something like that, whatever, right? This is all part of the process. This is the glossary. I'm not going to go over it. Exercise, verbose mode. Okay, so the following function uses pen up and pen down and moves turtle without using trail. Okay, so there's another function called pen up and pen down. There's a jump function where it just goes up and down, moves the turtle without like actually drawing a line. Write a function called rectangle that draws a rectangle with given side lengths. For example, here's a rectangle that's 80 units wide and 40 units small. You can use the following code to test your function, right? Yeah, very simple. Same thing with the rhombus. Do it again with a parallelogram. You can use the following code to test your functions. Exercise, write an appropriately general set of functions that can draw shapes like this. Jesus Christ, that's gonna be rough for someone new. I mean, honestly, it'd be kind of rough for me as well, because that's like a combo of math and like shapes and geometry and stuff, along with coding. So if you're really a beginner in programming, and what I've noticed is that there's actually a lot of people out there who want to get into programming and don't know basic math. It's not a lot of math you do need to know, but you do need to be able to teach yourself math and understand math, right? Which I think everyone has the capacity to do, but I think a lack of belief in yourself really stops people from doing these things, because it's not like super complicated math. Yeah, so just more shape drawing exercises. I'm chilling on that. There are several modules like Jupytertal in Python, and the one we used in this chapter has been customized for this book. So if you ask, it won't know which modules, but if you give it a few examples to work with, it can probably, okay, yeah, I would not recommend doing this virtual assistant stuff. I actually don't agree with this. Anyways, that's chapter 4. Got into some more details about functions, encapsulation, the concept of decoupling interface with implementation, because that's actually an important one. Making things more generic, which is part of why we use functions, is that we can have a reusable piece of code that we can break up and use in multiple ways and make it more generic. And, we can stack functions on top of each other. Lots of good stuff. And conceptually talking about things like refactoring and stuff like that. These are important things. Anyways, so I am going to now end this. Thank you so much. I am happy to see anyone who's here watching these things, because I don't think anyone is watching right now. All right, take care. We're going to move on to the next one in a moment, but you'll see it in 24 hours.